Welcome to Shanti-Peace for Mathematics. In this video, we will discuss about the Fourier Series. The Fourier Series is a starting point of very important subject called the Fourier analysis. And from the Fourier analysis, you can go to the harmonic analysis, which is very widely used to solution of partial differential equation. So here we are discussing about the Fourier series. The Fourier was a French mathematician and his time period is about the 16th century and the 17th century. While working on the heat conduction problem, he established this series. And later on this series is very much useful in the field of approximation theory, partial differential equation. So many mathematicians as well as the engineers are using this Fourier series in their research area and to develop the certain things. So here the idea is the Fourier series actually approximating the periodic function in terms of a simple function. The simple function, namely it is the sine function and the cosine function. This trigonometric system is orthogonal system. And allowing the computation of the coefficients of the Fourier series is used to well-known Euler's formula. And the Fourier series are very important for, as I talked, that it is about the engineers and the physicists because they allow the solution of the ordinary as well as the partial differential equations. There are other approximation series you probably come across with the function. So for example, the Taylor series is there. So if you want to calculate the Taylor series, the function you required is the n times continuously differentiable function, and then you can able to write down your series as f of x is equal to summation n running from 0 to infinity f nth derivative of that at the point x0 upon n factorial into x minus x0 raised to n. So this is the approximation of the function is there. But when you want to calculate the Fourier series of the function, it is not required that the function is a n times continuously differentiable function. So in the Taylor series, you are expecting the function behave a lots of things, not only function, but its derivatives also behaving the continuously. But in the case of Fourier series, you are not required that the function is even though continuous. For discontinuous function, also you can obtain the Fourier series of the function. So it is much fundamental and very useful in the field of approximation theory, in the field of Fourier analysis, in the field of harmonic analysis. So before defining the Fourier series, I required certain concept to develop. So let us go through that concept and then go to the definition of the Fourier series. The first concept that I required is the period of a function, or I can say a periodic function. So what do you mean by a periodic function? A function f is defined over almost all the points of real line. It is called the periodic function if for some positive number p, where f of x plus p is equal to f of x, for every x, if it is there, then we can say that f is a periodic function, and the p is called the period of the function f. There are examples of periodic functions are there. For example, sine x is a periodic function with the period 2 pi, because you know that sine of x plus 2 pi will again you will have sine x for every x. Same way, cos function is also a periodic function. Tan is also a periodic function. A tan is defined except countably many points, because it is not defined all the points where x will be 2n plus 1 pi by 2 for n belongs to z. The function tan x is not defined for that, but still tan x is a periodic function. There are functions which are not periodic. For example, x is not periodic function, e power x is not a periodic function, and so on. So there are other functions which are not periodic functions. The smallest number p, such that f of x plus p is equal to f of x, it's called the fundamental period. For example, if you have f of x plus 2p, if p is a fundamental period, then np is also a period for the function f. For example, if I can consider f of x plus 2p is equal to f of x plus p, then this will be f of x plus p we can write down, and that is by definition it is f of x. So 2p is also a period of the function if p is the period. So in the similar manner you can prove that x plus np is equal to f of x is also a period of the function f for all x. One more remark I want to say here, if f is a function with the period p and g is also a function with the period p, then you will have a function f, a into f plus b into g, where a and b are the constant, is also a function with the period p. Next, if I want to say that this 1 is a function which is a periodic function with any real number, because 1 is a constant function and which is a periodic with any period. Cos 2x, sin 2x, cos nx and sin nx are also a periodic function with the period 2 pi. Now using this cos x and sin x, we will define one series is called the trigonometric series. A trigonometric series is defined like this: a0 plus summation n running from 1 to infinity an cos nx plus bn sin nx. This trigonometric function is also a periodic function with the period 2 pi. And this expression that is here defined is about the trigonometric series is frequently used in Fourier analysis. So now we are able to define what is the definition of Fourier series. So to define the Fourier series, I may require a function is to be Riemann integrable function. So I am just taking f as an Riemann integrable function. See here I have defined that Riemann integrable function. What do you mean by a Riemann integrable function? You will going to discuss about the Riemann integrable function in your further study, but or instead of you don't want to use a definition of the Riemann integrable, you can just take your function will be having the countable many discontinuity in its domain, or I can say a function is a piecewise continuous function. Piecewise continuous function means it is having the discontinuity which will be a countable many discontinuities. So I am taking the function which is Riemann integrable on the interval minus pi to pi. Then the Fourier series of f is defined as a series a0 by 2 summation n running from 1 to infinity an cos nx plus bn sin nx, where this a0 is 1 upon pi minus pi to pi fx dx, an is 1 upon pi minus pi to pi fx cos nx dx, and dn will be 1 upon pi minus pi to pi f of x sin nx dx. This a0, an and bn are called the Fourier coefficient of the function f, and it is denoted by f is equivalent to a0 by 2 plus summation n running from 1 to infinity an cos nx plus bn sin nx. Here we have used the symbol is in this expansion, it is not actually equal to f, but this is because we have not yet established the convergence of this series to the function f of x for some value or for all values in the interval minus pi to pi. So before we need to discuss the convergence of that series, that we will discuss in my next video. So that's why we have used this notation here. So that is the definition of the Fourier series. So So definition of the Fourier series is this. If you have f, which is a Riemann integrable function and which can be expressed in this form. Now to prove the convergence of this series, I required certain results to prove it. I am going to give you as an exercise for that identities, and you can try for yourself. The first one is integration from 0 to 2 pi sine nx dx is equal to 0 for every n running from 1 to infinity. The second one, 0 to 2 pi cos nx dx is equal to 0 for every n running from 1 to infinity. The third one is the orthogonality condition for cos. It says that cos mx plus cos mx is 0 if m is not equal to n, and it is pi if m equal to n. The fourth one is same, the orthogonality condition for sin mx and sin nx, where m and n are integers which having the same output. It is 0 if they are not equal, and same if it is equal, then it is pi. The fifth one is 0 to 2 pi. It is sin nx into cos mx dx will be 0 for all m and n belongs to n. So these 5 results you can try yourself, and we will going to use this result in my next video to prove the convergence of Fourier series. So what do you mean by periodic function? As we have discussed that it is the f of x plus p is equal to f of x for every x which is true, then p is for the period of the function. We have defined the fundamental period, which is nothing but the smallest value p which satisfying this condition. Then we have defined the trigonometric series, and then using the trigonometric series we define the Fourier series. That's it for this video. If you like this video, please press the like button. If you have any comment, suggestion or a question, please drop down in the comment box below. See you in next video. Till then, bye bye.